All right, so the next derivative rule we're going to focus on is the quotient rule. So this allows us to take the derivative with respect to x of f of x over g of x. So the rule is as follows. So you take the denominator function times the derivative of the numerator, subtract the numerator function times the derivative of the denominator, all over the denominator squared. Or a mnemonic device I use to remember this is low d high minus high d low all over low squared. And so when I say high, d high, that's the derivative of the high function, and then d low is the derivative of the low function. So once again, low d high minus high d low over low squared. So this is the way I remember the quotient rule. So let's apply the quotient rule though in part A. So okay, we want to find the derivative of y. So dy over dy dx. So take the low function times the derivative of the high function minus the high function times the derivative of the low function all over the low function squared. Okay, and then we typically try to clean up the numerator, and we'll cancel anything we can after we see the factors of the numerator. So a lot of times we won't end up actually canceling anything. So what is that? Minus 10x plus 4x all over x squared plus 1 squared. Combine, let's see, 5x squared minus 10x, or minus 10x plus 4x is minus 6x plus 5 all over x squared plus 1 squared. Okay, so that's our derivative. And so there's nothing that will factor out of the numerator that will end up canceling with any of the factors of the denominator, so we'll leave it like that. Okay, let's try part B. Okay, so we're going to find the derivative of f of x. And, okay, same thing. So low function times the derivative of the high function minus the high function times the derivative of the low function all over the low function squared. All right, and we're going to distribute out what we can. Combine like terms in the numerator. All right, we could factor out a 2 out of the numerator. Let's see. But, you know, nothing cancels within denominator. So, no, not dy dx. We'll make it f prime of x. Okay. So this is the derivative. I would have taken this as well since nothing canceled. All right, so we're gonna apply the quotient rule on C and D as well. So low d high minus high d low over low squared. Okay, so g prime of x. So the low function times the derivative of the high function minus the high function times the derivative of the low function. Okay. All over low squared. Okay. Let's see. So we can factor out an x squared out of the numerator. Or we can factor out negative x squared. Right? So we'd have x sine x left. Right? Plus 3 cosine x all over x to the 6. I think my parentheses are messed up. Yeah, that's what we meant to do. Okay. So, this x squared can cancel out here with 2 of those. So our derivative is equal to negative x sine x plus 3 cosine x over x to the 4th. Or you could distribute the negative to the numerator as well. Okay, so there's an example where a factor in the numerator actually cancels with something in the denominator. All right, on part D, let's see. Okay, h prime of x would equal the low function. Well, before we do that, let's rewrite this into exponential form. So x to the 1/2 minus 1 in the denominator. Okay, all right, now we can be able to apply the power rule where necessary. Okay, so we're going to take the derivative. We're going to use the quotient rule. So the low function times the derivative of the high function minus the high function times the derivative of the low function. Right, all over the low function squared. Okay. So we get x to the 1/2 minus 1 minus 1/2 x to the 1/2, right? Because you have common base here, so you add the exponents, right? 1 plus negative 1/2 is 1/2. All over the same denominator. All right, what else can we do? You can combine this, right, to be 1/2 x to the 1/2 minus 1. Okay, and then we can't have a fraction within a fraction, so that 1/2 coefficient is an issue. So what can we do to get rid of the 1/2? Well, we could multiply the top and bottom by 2/2, right? So what is that? What does that get us? So x to the 1/2 minus 2 over 2x to the 1/2. Oh, wait, can't do that. Breaking PEMDAS. We'll just leave it as 2 in the denominator. 2 times x to the 1/2 minus 1 squared. Okay, and you could totally change it to radical form if you wanted to. Okay, so we want to compare these functions in fractional form to when we would use the quotient rule or not use the quotient rule. So notice how the denominator is just a constant. So we could do the quotient rule since it is in fractional form, but it is easier just to factor out the 1/6 or just divide both of those terms in the numerator by 6. So we could see it as, okay, we have 1/6 x squared plus, 3/6 is 1/2 x, right? And then we could just easily apply the power rule to find the derivative. So that'd be, 2 times 1/6 is 1/3 x plus 1/2, right? So no need to do the quotient rule, right? You would get the same thing if you did apply the quotient rule, though. All right, B, same thing. We can just see this as 9/5 x to the negative 2, just rewriting it. So we don't have to use the quotient rule. So we'll use the power rule. So f prime of x would equal, right, negative 2 times 9/5, negative 18/5 x to the negative 3. All right, so let's practice finding the equation of a tangent line. Okay, so we have this function, this rational function, and with rational functions, you can see where the quotient rule is helpful to find the derivative. So 3 comma 2, we're trying to find the equation of the tangent line. So just as a visual of what we're trying to find. So what's the first thing we do? We try to find the derivative. Okay, so we have to apply the quotient rule. So the low d high minus high d low over low squared. So the low function, right, times the derivative of the high function, right, minus the high function times the derivative of the low function, all over the low function squared. All right. And we'll clean it up. So we got 2x cubed minus 8x minus 2x cubed minus 2x, right, all over combine like terms. Okay, so we want to know what is the slope at 3. So we're going to plug in 3 into the derivative. So what is that? Negative 30 over 9 minus 5 is 5. 5 squared is 25. And we get to simplify that to be negative 6 over 5. Okay, so we have our slope, right? So our equation, following the point slope intercept form, right? So y minus the y coordinate of the point times equals the slope that we just found, negative 6 over 5, right? Makes sense because the tangent line has decreasing slope. Times x minus the x coordinate, 3. All right, so an automobile's velocity starting from rest is given by that, where v is measured in feet per second. Find the acceleration function, and then find the acceleration at t equals 5. Okay, so we know the acceleration is the derivative of velocity. So we have to apply the quotient rule. So low derivative of the high function, right? Low d high minus high d low, derivative of the low function, all over the low function squared. Okay, simplify, right, the numerator. Okay, those 200 t's are going to zero out. Okay, so our acceleration function is 1,500 over 2t plus 15 squared. All right, and then they want us to find the acceleration at 5 seconds. So let's plug it in here. All right, so this equals 1,500 over 625, right? 25 squared. And this is 2.4. And then the correct unit. So since it's acceleration, feet per second squared. All right, on this page, we're going to go over the rules for the rest of the derivative, for the rules for the derivative of the rest of the trig functions we haven't covered. So we've talked about the derivative of sine and cosine so far. Okay, let's derive the derivative for tangent x. Okay, so we know from pre-calculus that we can rewrite tangent as sine x over cosine x. Okay? And so since we're familiar with those two derivatives, we can use the quotient rule, right, to find the derivative of tangent. Okay, so let's do this. So the low function times the derivative of the high function minus the high function times the derivative of the low function all over the low function squared. Okay, so you might recognize that there is a trig identity in the numerator. Okay, so this expression is equal to 1. And what's the reciprocal of cosine? To clean it up, secant. So the derivative of tangent is equal to secant squared. So let's write these. So, a similar proof would bring about these other derivatives for the other trig functions we haven't covered, the reciprocals. So the derivative of cosecant is negative cosecant x cotangent x. Okay, the derivative of cotangent x is negative cosecant squared x, and the derivative of secant x is secant x tangent x. And yes, we do have to have these memorized. All right, so let's find the derivative of these equations. Okay, so the derivative of 3x is just 3, right? And then the derivative of tangent x is secant squared x. All right, on B, we have x times secant x, so we have to apply the product rule here. So, okay, so y prime is going to equal the derivative of x is 1 times secant x plus x times the derivative of secant x, which is secant x tangent x. And we can just drop the 1. Now, we could factor out a secant x out of both terms, but it's okay to leave it like this. Okay, on part C, we want to apply the quotient rule. Okay, so y prime equals, okay, low d high, the derivative of the high function is sine x, minus high d low, right, all over the low function squared. Okay, so let's clean this up. Okay, sine squared x, what is that? Minus cosine x plus cosine squared x all over sine squared x. Let me see. I'm going to get rid of e just so I have more room. Okay. So that, what I have highlighted, is equal to 1 by that Pythagorean identity. So we got 1 minus cosine x over sine squared x. So we could break that up into 2 fractions, right? That would be like 1 over sine squared x minus cosine x over sine squared x. And let's see, 1 over sine squared is cosecant squared x. And cosine over sine squared, we can see that as cosine over sine, which is cotangent. And then we'd have 1 over sine x left, which is cosecant x. Okay, so this looks about as good as we can get it. We could factor out a cosecant x out of those 2 terms, but that's okay. All right, D, okay, y prime equals, okay, so the derivative of cosecant x is negative cosecant x cotangent x. And then the derivative of cotangent x is negative cosecant squared x, so minus a negative, make it a plus. And yeah, that's it. That's all we can do with it. We could factor out a cosecant x out of both terms, but that's okay.